So this lesson ties in with direct variation. This is actually called inverse and combined variation. So as we said, direct variation, if one value is increasing, the other value is increasing, or if one value is decreasing, the other value is decreasing. Inverse variation is kind of backwards to that. So with inverse variation, to say they vary inversely, what we mean by that is one quantity is going to be increasing while the other quantity is decreasing. A lot of times, like if you ride a bike, if you're trying to get home, the faster you ride your bike, the quicker you're going to be able, the shorter the duration it is on time to get home. So the amount of time to get home actually decreases. Or if you're driving a car at this day and age, the faster you are able to drive, then the distance it takes, the time it takes to cover that distance is actually decreasing. Sometimes in cooking, if you crank up the temperature on something, increase the temperature, the length of time in cooking actually decreases as well. So those are some things that I can think of. Also, if you think about like on the job, if I were to increase the manpower for a job, the length of time to complete the job would actually decrease. So how long it takes one person to do a job, and then if I add on another like 4 people, hopefully with 4 people, the amount of time it takes to complete that job actually decreases. So that's described as inverse variation. So in a word problem, if one is increasing and the other is decreasing, we actually have to be using an inverse variation strategy. To set up an inverse variation problem, we have to identify the 2 pairs related. So arrange one pair as the numerator of one ratio and the denominator of the other ratio. Arrange the other pair so that the ratio contains like measures. So form a proportion using the ratios. So what that kind of means is, let's look at an example, see if we can put this together. So 5 machines take 12 days to complete a job. How long will it take for 8 machines to do the job? So notice how, it takes 5 machines $12 days. How long will it take 8 machines? So notice how I have machines today. So the 8's got to go over here on this side. 8 machines is going to take how many days? So what they're saying to do here is, when I write my proportion, the 5 machine is going to be the numerator of one. The 12 days becomes the denominator of the other. And therefore, the 8 and the 12, or sorry, the 8 and the x will stay in the same direction. So that's how I went machines to days. So the 8's going to go here, and the x is going to go up here. So notice how when you create the proportion, the 5 and the 12 don't go straight across. They kind of go across of each other. One's a numerator, one's a denominator. So if I want to solve this, I can cross multiply. I get 8x equals then 5 times 12 would be, what's that? 60. If I divide both sides by 8, 60 divided by 8. Let's see here. That's going to give me 7.5. So it's going to be x equals 7.5 days. So sometimes we may have to round. I don't think that's a round. I think 7 days is probably an acceptable answer here. So if I had 8 machines, it would take me 7 days to complete the job. So again, some people might say, well, you can't work a decimal a day, so you have to count that as a whole day. So you'd have to maybe round that up to 8 days as well, depending on the situation. So gears and pulleys, a lot of times what we pick up on is they have an inverse relationship. The speed and size of gears and pulleys have what we call an inverse relationship. Suppose a large gear and a smaller gear are in a mesh. a larger pulley is connected by a belt to a smaller pulley, the larger gear or pulley is going to be at a slower speed. The smaller gear or pulley is going to be going at a faster speed. So that kind of makes sense. We kind of see that the bigger the diameter, the slower it goes around. The smaller the diameter, the faster it goes around. So there's an inverse relationship there. So in industry, we have a 10-inch diameter gear is in a mesh with a 5-inch diameter gear. If the larger gear has a speed of 25 RPMs, how many RPMs does the smaller gear turn? So again, we have to pick up on that gearing has an inverse relationship. So as I picked up on this, the big gear is 10 inches in diameter, and it's going at a speed of 25 RPMs. The smaller gear is the 5-inch diameter, but we don't know how many RPMs that's going. So that's my relationships, the known and the unknown. As far as the proportion goes, notice that the 10-inch will go on the top on one side, but the 25 actually goes on the bottom of their side to create what we call an inverse relationship. So the 10 inches goes on one side, the 25 RPMs goes on their side. And then the 5 inches has got to stay on the same side, 5 inches, and the X RPMs goes over here. So we have that kind of going on. So if we solve this, we have then 5X equals 250. Then how many 5s go into 250? So 5 goes to 25, so 5 times, so that'd be like 50. So that's equal then 50. So the smaller gear is actually going 50 RPMs. So that's like revolutions per minute. So 50 revolutions per minute for the 5-inch gear. Notice again, the smaller gear is half the size of the bigger gear. So it should go twice as fast. So if the bigger gear is going 25, the smaller gear should be going twice as fast. So that means it should be going 50 RPMs. So that kind of makes sense as well. That since they do have a relationship that are being twice the size of each other, the speeds should be kind of in that relationship as well. So using the constant of variation to solve problems, the constant of what we call inverse variation, the constant of inverse variation is actually going to be k equals xy. Remember, in direct variation, it was k equals y over x. In inverse variation, it's going to be k equals xy. So the formula for inverse variation is going to be y equals k over x. So notice the formulas are a little bit different than direct variation. So we have a new formula, y equals k over x, is going to be used as a shortcut for inverse variation problems. So let's see if we can piece this all together. So a landscaper needs a 5-person crew to complete a commercial project in 30 hours. How many hours will it take the project for the following number of workers? 3 workers, 8 workers. So we do have a way to find the constant of variation because we have some known facts up there. So notice that the constant of inverse variation is going to be the independent variable times the dependent variable. So notice how, again, how many hours we're looking for to complete the job. So the hours, since that's what we're looking for, is going to become our y value. This is going to be our dependent variable. So the number of people in the crew is going to become our independent variable. So here, the 5-person crew times the 30 hours is going to be our constant of variation, which is going to be 150. So it's going to be 150, what we call like man hours, if you will. Or person hours. So if I can now see if I can put this all together, we're going to have now to find part A here. We have our formula is going to be y equals k over x. So where, again, y is going to be the number of hours, since that's what we're looking for, and the workers is going to be our independent variable. That's our input value. So notice how it's going to be 150 divided by 3 workers. So if I divide 150 by 3, that would be like 50 hours. So notice that, 5 workers took 30 hours. So 3 workers should take more time. So 50 hours sounds reasonable to that problem. So if I do part B, we have y equals kx is our k over x is our formula. So we have y equals then, again, our constant of inverse variation was 150 divided by, this time it's going to be 8 workers. So 150 divided by 8. That's going to be 18.75 hours. So 18.75 hours. So notice that, again, 5 workers took 30 hours. 8 workers should take less than that. So 18.75 hours sounds reasonable. So that's how we can use a formula to solve that problem. So some problems are what we call combined variation. There's direct and indirect involved. So notice that if we say y varies directly with x and inversely with z, notice how we have x is going to be the direct variation, the z is going to be the inverse variation in this, where k is going to be our constant of both, of the combined. So if z varies directly as the square of x and inversely as y, find z when x equals 8, y equals 15, and the constant of combined variation is 12. So in our formula, since we're asked to find z, that's going to be here, and that's going to equal then k times our direct variation, which we're using, in this case, it's varying directly as the square of x. So the square of x is going to be x squared over then, and inversely with y, so the y is going to be on the bottom. So we have that kind of set up here. So to find z, we're going to have the constant of combined variations to 12. The x is going to be squared. It's going to be 8 squared. And we're going to be dividing by the 15. So we put that into the calculator. So we have, I'm going to use the alpha button. So alpha, we have 12 times 8 squared on the top. Oops. And divide that by 15. That gives us then 256 divided by 5. Let's just make that a decimal. So it's going to be 51.2. So it's going to be our value for z, 51.2. So see if we can do another one that's combined, where part of it's direct and part of it's inverse. So the number of hours that it takes p persons to assemble m machines varies directly as the number of machines and inversely with the number of persons. 3 persons can assemble 10 machines in 5 hours. How many persons would it take to assemble 36 machines? So based on the problem, it says the hours is going to vary directly with, so we have the hours it takes p persons to assemble m machines varies directly as the number of machines. So notice how the number of machines is going to be varying directly with the hours, and it's going to vary inversely with the number of persons. So notice that the number of machines is going to increase as the hours increase, and then the number of persons is going to actually go the other direction with this. So 3 persons can assemble 10 machines in 5 hours. How many persons would it take to assemble 36 machines in 8 hours? So we have a lot going on here. So let's unpack this. We have 3 persons, 10 machines in 5 hours. What we don't know is the constant of variation on that first part. So what we can do is we can substitute the 5 in for H. The constant of variation we don't know. It took we have 10 machines, and then we have 3 people on the bottom here. So I can put this as like 5 over 1. So if I solve this, we have like 5 over 1 equals 10K over 3. Notice how this is a proportion. We can cross multiply. So this is going to be 10K equals 15. If I divide each side by 10, that's going to be a 1.5. So our constant of combined variation is going to be a 1.5. So what I can do now is I'm looking for the number of hours, or actually I'm looking for how many persons it would take to assemble 36 machines in 8 hours. So what I do know now is in our formula, we have the hours varies directly with machines and inversely with people. So the constant variation we do know now is the 1.5. So we have 36 machines in 8 hours. So if I substitute in our formula, we know the 8. We know the constant variation is 1.5. We know the machines is 36. But we don't know is the number of people. That's going to be down here. So again, I can make this a proportion by putting that 8 over 1. So again, I clean up the top. I'm multiplying 1.5 times this 36. That's going to give me this 54. So I have 8 over 1 equals 54 over P. We can cross multiply and get 8P equals 54. If I divide both sides by 8, so if I divide that by 8, I end up within 6.75. So P equals 6.75. But notice that as far as persons go, we can't have 6.75 persons. So that has to round into P equals 8 people, or I'm sorry, 7 people, 7 persons. So we can't have a decimal of persons. So we have to round that up to 7 persons to complete that job. So that's kind of a little bit of an insight of how we can do inverse variation and also combined with direct variation.